Hi, my name is Mike Kilroy, and welcome to our interview with Mattia Fiorentini, Head of Machine Learning and Quantum Algorithms for Cambridge Quantum Computing. We're here today to talk to Mattia regarding his team's recently published scientific paper regarding new thoughts in quantum machine learning. Hi, Mattia. Thank you so much for joining us. It's a pleasure to talk to you.
Hi, Mike. Thank you very much for having me.
Absolutely. I was wondering if you could maybe just briefly describe the main takeaway from this research that you've done.
Surely. So, we have demonstrated that a quantum computer can be taught to reason. That is mainly answering question and making prediction in uncertain condition and in cases where the full information is only partially available. The reason why that is quite interesting and exciting is that these are the typical scenario that describe most of the decision making that happens in real life. Decision making is not easy. It's not an easy thing both for computers and humans alike. But the difference is that humans do this all the time with different degrees of success, while instead computers generally speaking don't do this naturally or intuitively, and it takes them a sophisticated theory, a lot of data, and large amount of resources to do that. We show how these tasks can also be formulated in a quantum-friendly way, and indeed solved by a quantum computer.
Wonderful. Can you tell us a little bit more why it's so difficult for classical computers to do reasoning?
Formalizing reasoning is difficult in general. Again, the key aspect is about managing uncertainty. And there are two key components to that. The first one is being able to assess the quality of your information. So how much something that you believe is true or false is actually true or false, right? The second aspect instead is making projection about future scenario and being able to distinguish about likely, unlikely scenario and to make educated guesses on the risk and the reward of each one of the cases. Also, there is a bit more of a technical aspect, which is that most of the decisions that human makes are binary decisions, yes or no decision. Like, if something has happened, then this is my next step. If something didn't happen, then I'll do something else instead. It turns out that managing say long chain of yes or no outcome is particularly complex for classical computers specifically.
Got it. Can you tell us a bit more regarding these pioneering results that your team has obtained in quantum machine learning?
Absolutely. So, in our latest paper, we focused especially on the problem of inference in reasoning models, such as Bayesian network. Why this is interesting? Because Bayesian network are models that are very flexible and that can describe very well complex scenario and situation. And the inference problem itself is about making sense of those models. Again, asking and answering question and being able to make prediction with uncertainty estimate based on those. To achieve this goal, we first had to extend the theoretical framework of variational inference to be able to apply it to quantum computer tools. The second step was to really code up, let's say, the theoretical aspect into quantum code and show that quantum computer can indeed perform variational inference of probabilistic modeling, especially the quantum computer that are available today to the scientific community.
Is this the first time it's been shown that quantum computers can learn to reason?
To the best of our knowledge and our research, yes. This is the first time that quantum computing is used to perform a variational inference of a probabilistic graphical model.
Yep, absolutely. Can you explain how your proofs in the paper can help solve classical machine learning limitations, like the need for huge training data sets and these energy-hungry algorithms?
Specifically to quantum machine learning, we have some results already available to us that show that quantum machine learning algorithm, for the very small resources that they are allowed to use, so 4-5 qubits, and consequently the very limited consumption of power that is needed to manage again 4-5 qubits, they can achieve state-of-the-art results on certain machine learning benchmark against comparable classical method. That's the key, against method that are classical but can be compared to quantum one, right? Usually, so what do you expect out of this? We expect it as a quantum computer will scale as a quantum machine learning model become more complicated. Smaller quantum model will be as good as producing certain result as classical one, therefore consuming less electricity. But smaller model also require, generally speaking, less data to be trained.
Thank you for that. Could you provide maybe our viewers a couple of specific real-world applications of quantum machine learning applying reason?
So in the paper, we focused on Bayesian network, which are a type of probabilistic graphical model. We focused on a case of medical diagnostics, which is relatively realistic, and a case of financial forecasting for aiding investment decision. Other very interesting scenario are the one of the predictive maintenance of complex industrial apparatus. Typical example is the one of a jet engine. So in predictive maintenance, what you want to do is that you want to connect the status on the individual component of a complex system, which can be monitored easily, to the overall working condition of the full apparatus of the jet engine. Clearly, if a piece of this apparatus fails, the whole engine fails. But we don't want to let the system fail and then fix it. With this Bayesian network, we can perform variational, we can formalize, let's say, the structure of this complex machinery, encode it as a Bayesian network, and then we can perform inference, on this network, and ask, given the question on how likely the engine how likely is the engine to fail, so we can reconstruct the bigger picture that it's in the status of all the individual components. I know that also inference and causal inference in particular is used for modeling biological system, to model the reaction of certain tissue that have disease in them, to certain drugs, and to understand also the cause-effect relationship between genes, diseases, and the efficacy of a drug, right? Again, that's a scenario in which variational inference can be applied. The last notable example that I would like to mention is the case of natural language processing, right? Having a machine that can parse a text and then ask and then answer high-level question about, if certain actions were indeed completed or not, of certain topics were mentioned, if certain decisions were made. Think about, parsing the proceeding of a meeting or things like this, or a contract even. These are quite very useful tasks. A lot of man hours are spent just to reviewing these long documents.
That's very fascinating stuff. How soon do you think we might see some of your proofs in the paper lead to real world implementations? Especially will we see them in this NISC era?
The key point here is, I think, the following: the case we were able to solve in the paper, I think they're quite realistic, right? Roughly speaking, there is a correspondence that one qubit can encode the outcome of one binary variable. The qubits that we are available today are, I mentioned it earlier on, are 50 plus. That's the largest number of qubits that we are available, and we could easily use through the quantum cloud, let's say. So a model of reasoning Bayesian network at a 50 plus variable is not a textbook example anymore. So it would be a case that it's already quite realistic. So I suppose that there is nothing that today, if we accept that 50 variables are enough to make, to study a system that is not trivial anymore, then there is literally nothing to prevent us studying that, apart from just going there and trying to do the work.
What response would you like to see from machine learning scientists and quantum algorithm specialists to your paper?
So let's start with the machine learning scientists. So to them, I believe that in summary, in short, we are offering new tools, both theoretical and practical, to investigate some of their more tough and ambitious problems. As I mentioned, to me, this is the first time that quantum computing was a real quantum computer was shown to be able to perform successfully variational inference. Sometimes old and complicated problems just needs a new tool to be studied and hopefully to lead to new answer. That's it. For the other community instead, for the community of the quantum scientists, we believe that we have shown that via probabilistic modeling and by performing inference of them, we can make quantum computing relevant to a whole new field of application.
Final question: what's the key takeaway for businesses looking to explore quantum machine learning and quantum computing more generally?
So in summary, I believe that each large corporation that rely on consuming large amount of resources, of computational resources for implementing their processing, delivering their services, or really, in the tech sector, you can think that everything is done by computers. Should be interested in partnering up with the quantum computing companies, hardware and software, and let's say engaging in proofs of concept, which could lead to large benefit and which have benefits that I think outweigh the risk, which in general are quite small, especially in software project, because again, I think that most of the companies really will consume quantum computing as a sort of software product. They won't need to buy or manage quantum computers.
Well, thank you so much, Mattia. Really appreciate all your time, and wonderful job by you and the team on this paper. And thank you for all your informative comments. And just want to remind everybody that if you go to the Cambridge Quantum Computing site, which is cambridgequantumcomputing.com, it'll have links to the paper that Mattia and his team have accomplished, as well as links to a Medium blog post that they've written as well to give you sort of a higher level explanation of what they've discovered. Thank you again.
Thank you, Mike, and thank you for asking me this very engaging and insightful question.